Morning. If you hear me, we are able to start. Today we are going to complete our exposition about cement and concrete. And this scheme you see on the left, to the left, represents the possible problems which are offered in concrete, which are encountered in concrete, and in concrete which is reinforced with steel bars. There are other options, starting from steel nets and possibly extending also to other possible materials, but still the best option is reinforcement with steel bars. The resolution is not that good, but anyway, I hope you are able to grasp the sense that we have a number of possible problems. We have the presence of moisture because one of the main points is that in concrete there is the presence of porosity, and the porosity means that the water is able to circulate, and this means that, as always, water is present with some salts. Some salts are present in water, and therefore we can easily think that they are going to produce some effect on pH, which, because it might be the case that they are not neutral salts, there might be basic, so alkaline, which in practical terms it's good for reinforced concrete. We are going to see why. Or we can be acid. They can be acid, which is much worse. So in practical terms, we have the effect of the presence of moisture. So concrete is a material for external applications, and in practical terms, this means that the material is supposed to be exposed to the external environment, and in the external environment there is moisture, which might be variable. There might be also the fact that temperature varies. So we have the freeze-thaw cycles. So we may have freezing at night, especially in some countries. This is a frequent occurrence, but also here on the Upper Nile, this is a frequent occurrence that in winter we have freezing at night. And then we can have also some thawing, so some heating operations which are performed closer to concrete, just by the effect of sun, or there might be other operations which, for example, the presence of heating, which in practical terms generate an increase of temperature in concrete, which has some effect. So freezing has an effect in terms also of change of volume, which in a material that includes porosities means that this can crack because of the expansion due to the fact that water, which is present in pores, becomes ice. This is obvious to understand, and this is unfortunately not the only problem we can have. The problem that we have is also connected with the presence of salt, and so change in pH, as I was saying. Some particular salts are particularly difficult to treat, like sulfate. Sulfate, so the salts from sulfuric acid in practical, so the ions from sulfuric acids, in practical terms, can be due to, for example, to the use of fuel, which results in acid rain result then in the presence of sulfate ions in air and in water. And in the soil, again, you might we can have also percolation in soil. In practical terms, we distinguish, well, you can see that concrete is a very practical field where the division, the partition of materials into different classes is quite frequent, and it allows to be more clear cut about what we want to use, but in other sense you lose some accuracy in some cases in doing everything by dividing materials into classes. Also, in terms of sulfate attack, we can divide into 3 types of sulfate attack, 3 levels of sulfate attacks, and this affects the water to cement ratio. So we know that water to cement ratio is the main factor in practical terms that you need to work on. It's the main factor also because you can control to a point the material, but once you buy it, the material is there to make concrete. You can control up to a point other situations. You may know the environment better than controlling it. You know that the environment is that one, that you are building in the mountains or you are building at sea, and this makes a lot of a difference. So you can imagine that chloride is present at sea. Whilst in the mountains, you may have frost attack. You need to make some decisions before starting building, but when you start building, what you need to control is the water to cement ratio. So this is in a sense, this is the controlling factor for everything that follows. And water to cement ratio controls also the process of drying, which we call cure. And by law, we are not allowed to use cement, to leave our, being more practical, to leave our cement or concrete, a reinforced concrete wall alone, standing alone, so uncovering it before 28 days. We are not allowed to do that. Having said that, it might be also the case that we need to prolong this period. This period might be longer, which in economical terms might be a problem because the best idea would be that in 28 days concrete is ready, our concrete wall is ready, because we have to carry on with the construction, with building. But in other situations, it's not possible. This is not possible because, for example, it depends also on the composition of the cement. As always, I give you some hints, some indications of some research teams which are present in material science. For example, 3-calcium aluminates are present may be present in cement, and they have an effect in sulfate attack, basically on the fact that they control quite a lot the expansion of the concrete, because in practical terms, well, this is not only typical of C3A, but it is true that you can easily see that 2 main phenomena are due to the presence of salts, also of sulfate attack in this case, and shrinkage due to freeze and thaw cycles. These 2 phenomena result in the propagation of crack propagation. Then the material might be tough enough to withstand cracks. And concrete in general terms is reasonably tough in most cases because it has crack. You can see if you look around in our cities and villages, we see a lot of concrete around with a number of cracks, but which stays there anyway, and it's solid enough to withstand the load. But as you may have realized by a few examples in our recent history, when the crack propagates, when the crack reaches the critical energy for propagation, therefore the stress intensity factor, then it propagates suddenly. There is no time for repair. So that's why we are a lot concerned about crack propagation, because the fact that the crack is there and it doesn't seem to move, apart that there are some possibilities to investigate if it is moving from a microscopical point of view, which are not always very practical to apply when the concrete is there in the construction. But apart from that, this doesn't mean at all that the crack wouldn't reach at some time its critical energy, and then the wall, the structure would collapse. Okay. The studies on concrete therefore involve a lot the question of voids and cracks. Voids are in a sense necessary in concrete because they allow the material to be set into its special mold, and then to be left alone when 28 days after removal. You may remember that the structure of cement from last time is mainly formed by this CSH gels, which means calcium silicate hydrate. So they are hydrated and they are constituted mainly by calcium carbonate and silica. That's the concept. But they are jelly anyway. They are gel. In fact, we discussed a lot about the rheology, how this gel, when the material is hydrated, perform and fill the mold, etc. And how well they are able to dry over time. Of course, there might be some crystalline parts. There might be some capillary voids which are some parts which allow the water to move around. So the water moves around because there are capillary voids. Then a lot of studies are important about the dimension of air which is able to be trapped into cement and withstand the effect of frost, because there are air bubbles which are trapped and which are less of a millimeter in practical terms, these bubbles, and we can have also some larger voids, which are really, of course, they are always filled with air. It's important, the influence of oxygen in reinforced concrete. It's important because we have steel bars, and we have steel bars which in principle are anodized. In principle, they have some, they suffer oxidization, but on the other side, this oxide is stable. You may remember aluminium or some types of steel. This is ferritic steel. It's typically ferritic steel, so it's an alpha iron into concrete. But on the other side, we hope that the oxide is stable, but in some cases might not be that stable. And then we can have some aggregation of cement particles, and this might represent a problem, also the segregation of cement particles because they form a harder part. But in another sense, they may stop crack from intruding into them, but on the other side, cracks can move around, and the K can be diverted, and which means, in practical terms, that they accelerate fracture instead of stopping it. And this might be due to inaccurate mixing. You remember that we work a lot on mixing of effective cement mixing, and which is regulated in very precise ways. So the clinker is produced with very customarily designed ovens, furnaces, in order for it to have the good, best possible ability to flow. And considering that it is not by any means a Newtonian fluid, so we have to convince it, push it in some ways to fill the mold. And this gives you an idea of the effect of the porosity. Porosity propagates in different ways, and this depends on, of course, during hydration, and it has some relation with water to cement ratio. So it develops with hydration, and it creates these nets of capillary porosities. There is, you may remember that water to cement ratio, the ideal water to cement ratio, which allows you to come to a complete hydration, is 0.42. Having said that, we could also work with lower values, and in practice there is another limit, which is the percolation threshold, which is 0.18. Below that, water is not able, is so little, is not able to diffuse in cement through the pore network, and the formation of capillary networks is necessary in a sense for the characteristic of the material to allow it flowing, etc. So the capillary porosity for the characteristic of the material itself needs to allow water to flow. But on the other side, you can see here that you have a connection. So a fraction of the cement which is completely connected, and which depends on the which is connected, which means that it has no pores. Basically, a part of which has no pores, and it's able to, and you are able to travel from one part to the other. Like that, all your cement is connected, so you are basically able to travel from, if you think of a wall, to travel from one side to the other with the wall without being stopped by porosities. But this is not always the case. In some cases, you have some porosity that stop you traveling. Imagine that, well, say that air bubble that wants to, or more than air bubble, that particle of calcium carbonate that commits, that wants to travel around your cement, your concrete. As always, remember please that concrete is a cement with aggregates, so with sand and with gravel and different other kinds larger substances, for example, the diatomaceous earth and so on. We may have also some volcanic lava, etc. And cement has normally no structural significance. In other words, we are not able to build a wall that stays together, that stands together so by just using cement. We need to use concrete for that. We can use cement for binding two different parts of the concrete, or binding, say, bricks, etc., bricks, stones, etc. Okay, so we have again this influence of water to cement ratio to try to clarify which is the degree of connection of the pores and therefore of the cement again. So the connection of the pores, of course, depends on the degree of hydration, and it depends on the water to cement ratio. You can easily see that if you have more water, you are supposed to be able to travel along the pores, or for all the dimension of your water. So when we talk about aggregates, of course, we can talk of aggregates. If aggregates have a dimension of less than 100 microns, we still don't talk about concrete. So concrete is a cement plus aggregate that has a structural significance. So we might have, in other words, we might have some aggregates and still not having concrete. We might have some small aggregates, some small aggregates. Yes, as the question that Francesco was posing, if I understand it well, the trapped air voids can be due to inaccurate management of the cement when it is processed in the mixer, because of course in the mixer you have, it's usually done in open air and you have some air coming in. So that's why we need to have a regulation of the dimension of the mixing velocity and of the mixing time, with the risk that more air comes in. And then what in practical terms, we have two exigencies which are in contrast. We need to have, after curing something which is structural, in 28 days we want to have something structural. In actual terms, at the very moment we are mixing everything, we need to have enough water to it is not to work it. It is not very different from making bread. In practical terms, you have some the need of having a mass which is can be worked to make the shape, to fill the mold if you have a mold, because you may have a mold also in bread making, obviously. But on the other side, you would like to cook it, to mix it, and then to cook it. And at the end of the day, you want to have something which is according to your requirements. So you need to act on in our case, on the water cement ratio, which is not very different from making bread. You may also add water to make the mass of the right consistency. It is a tricky question, but water cement ratio controls it all, because it is the only factor on which we intervene in the very making of cement. Here we have a granulometric curve of cement aggregates, and we have some aggregates. You can see that up to 100 microns, what happens is that these are not considered structural. As always, these are clear-cut divisions, which are regulated by law and so on. of course, it's nothing as precise as that, but we need to set the division at a certain point. We may assume that there is no, if the practical terms, there are no particles which are more than 100 microns diameter, which is already an assumption, because be aware that it's already an assumption that they are round, because in most cases aggregates are not round. They are elliptical if you are lucky. Otherwise, they have a strange shape, more similar to the rock particles, complex shapes, and so you assume an equivalent diameter, and you may say that if they are not particles which have an equivalent diameter of more than 100 microns, you are not allowed to use it as structural. So you have this kind of distribution. Of course, this is an example of this distribution, and basically you have these two curves, and according always as the Bible distribution, you can consider how it is far from a Gaussian curve. It's never very close to a Gaussian curve. There is always a prevalent distribution. This is already simple. This is already very simplified, because you might have two peaks, 3 peaks. Here you consider the quasi-Gaussian in a sense. Quasi-Gaussian in a sense that you have just one peak of your curve, and the curve is quite smooth. So it tends to go towards the peak, and it tends to decrease when you go away from the peak. But it's just to give you an idea what happens when you study cement. Of course, before putting on the market, for example, bags of aggregates, we try to understand which is the distribution. Of course, the mass distribution of aggregates. This is done in this case is done just for a cement binder. Of course, if you have aggregates which are larger, it's less workable, but it has more compression strength. Consider that for binders don't always work for compression. Binders, if you think of a binder between two bricks, the binder works a lot into shear, because it might be sheared away, and the two bricks might separate, because it flows on the shear direction. It's not able to withstand shear, which occurs because the walls move, and if you consider an earthquake, but even you might only just consider traffic vibration, then the binder might move into shear, which is a problem, and which we need to predict, for example, by controlling by reaching an optimal equilibrium between our distribution and the characteristic we want. This is complicated further in the last few years, because we started to introduce more and more aggregates which are made from waste. We take waste from somewhere. For example, we demolish a house, and we get some particles of stones, of bricks, and so on, of sand, gravel, etc., and we put into the new construction. Then we need to ensure that the binder works. So there are some curves which are even more scientific in a way, and which is the Bolognese curve. As always, you know how material science works. We start from an ideal situation. Well, it's not very different from some fields of think of gas chemistry. It's the same, of gas physics. We start from an ideal situation. The ideal situation is represented by the Bolognese curve. The Bolognese curves indicate which is the distribution. Here we are on the other side. we are to aggregates which are tangentially an equivalent diameter of more than 100 microns. You can see we get up to 19 millimeters of equivalent diameter. So chunk of stone or gravel, etc. And we can say that we have a parameter which is A. A is a constant. This is, again, it's a technological test. So it's a test made on the real material without calculating, this is a probabilistic study, without calculating the, for example, physical characteristics like strengths and so on, but what we calculate in reality is just the probability of to understand which is the ideal distribution of aggregates. And the construction of these curves is not that easy, because how do you decide which is the equivalent diameter of the maximum diameter? Is easier to make the maximum diameter when you come to because the equivalent diameter is more simpler in terms of in physical terms to understand the equivalent diameter. But in practical terms, what you do to measure the diameter of aggregates, you put them down a sieve and you see how many pass and how many don't pass. You know the dimension, you know the mesh of the sieve, and then you realize that what doesn't pass has a maximum diameter, which is higher than the dimension of the sieve. Otherwise, if they pass, their maximum diameter is less than the dimension of the sieve. And we use sieves, a number of sieves. Of course, we don't use passing from theoretical physics to this kind of work. You may easily understand that we don't have infinite sieves. We have a number of sieves. There are also standards on the number of sieves that has to be used, which is a discrete number of sieves, and it gives rise to, in this case, you have, for example, you have 1, 2, 3, 4, 5, 6. Basically, I see 6 sieves. In fact, you see that you have 6 parts of the curve, and basically you have 6 experimental points. And then you have these A, this which is, these are experimental curves which are then translated into probabilistic dimensions, which is, it depends on the type of cement, type of aggregate, which is not natural. Natural aggregates are extracted down a cave, which means that they are rounded by the action of time. They have become rounded. Think of the gravel you take in a river. There are less, well, in a sense, luckily, we use less and less natural aggregates. We use more and more sort of I would say I wouldn't say synthetic, because it's not true. They are not really synthetic, but they are crushed from something else, from the demolition of another building or from other operations. For example, there might be waste. You might have a marble cave. You extracted the main pieces of marble, and you might have a lot of powder going around, and you might intercept them and aggregate yourself. This is becoming a large trend, putting aggregates into cement where we have some waste which might be useful, and reduce the price, of course, because consider that we have the big chunk of marble which might be go to somewhere to make some pieces also precious, etc., with some value, which means that waste is worth nothing, and may use it to reduce the price in some other operation, for example, making concrete. But the question there is paying for transportation, because these operations are good because if they are made at 0 kilometers. Otherwise, with this kind of operations are usually made on site. Also, cement is mixed on site because it changes properties if you transport it, and that's a problem. And also because you need to be able to intervene and, for example, adding more water if needed. Of course, you cannot make it somewhere else and transport. That's a main limitation with concrete. But what you can transport are aggregates to make concrete that you can transport, and of course steel bars. You buy it and they are already there waiting for the cement to come, for concrete to come into your room. You can have A, which depends on the type of cement which you are using. B is the sieve dimension, and D capital D max is the dimension, is the maximum diameter of your aggregate. You can have also the consideration of Fuller curves in case A is equal to 0. And basically, if A is equal to 0, you might have a distribution with minimal void content. You may suppose to have a minimal void content. Of course, we move above Fuller is a bit ideal, because if we have minimal void content, it's very likely we are not able to work our clinker to make it, our clinker with aggregates and so on, to make concrete. So we have some other technological tests which are interesting, and I show that because it gives you an idea of how these things work. These are very simple tests. They are not very precise in physical terms. It's like the comparison might be with hardness tests. Hardness tests are very important because they are cheap and fast. Slump test, it's again cheap. It is not as fast as hardness, but considering the amount of material which is involved, it is important, because once you decide, as always, that the curves are orientatives of some studies, but they give just you just an idea of how the thing works. Basically, we have this pile, this troncoconic pile of materials which are put together into making concrete. What we want to see here, we want to see here whether our concrete would collapse, because one occurrence into concrete, it's something that happens, is that the wall collapses before ending cure period, even in some cases later on, but in most cases during cure, because it's drying, and water is coming out, and coming out, it's reduced the water vapor depending on the temperature. Anyway, you have this kind of percolation, and the wall collapses under its own weight, which doesn't happen. Well, this is different in terms of material. This doesn't happen with steel. This wouldn't happen with plastic. This happens with cement. This might happen with cement. To avoid that, we have this lump test. So basically, we have this conical. In reality, it's troncoconic, but they call it the cone. You can see the inaccuracy of this physical. Forgive me, but this is inaccurate, but works. In reality, it's troncoconic, and you beat 25 times with that steel rod. Of course, we have standards. We are not allowed to use any size of steel rod. There are standards that give you the dimension of the steel rod you have to use, even the type of steel you have to use. But apart from that, you have this pile of material, and you beat 25 times, and it decreases a bit. It decreases a bit. It tends to expand. Of course, this is not an operation we do usually with walls beating with a steel rod, but here we have still a pile of materials for concrete, for making concrete. But we want to know the consistency class. So basically, we have this concrete which has already been prepared, not put in a mold. It has already been prepared. It just there is just this Abraham cone which allows it to stay together, but it's not completely sealed. So it's prepared as concrete, and then we have this slump. Slump, of course, depends on water to cement ratio, because the highest the amount of water, the highest the slump, so the more it goes down. And it depends on the consistency, because we have some consistency classes, and the more the material goes up into consistency class, the more it's workable. In some cases, we need some fluid or superfluid cement concrete. It depends on the kind of structure we want to make, because we can give some more responsibility on steel, in a sense, because it depends on the thickness of the structure we want to make. It depends on the geometry we want to make, because we might have some curved geometries in made with concrete. Concrete doesn't work exceptionally well on a curved structure, but it has been a trend in the last 60 or 70 years to try to make it more curved, even with the bag quite thin. Probably it's not an objective that applies well to concrete, but reasonably thin structures, giving some tensile strength, even some flexural strength, working with aggregates and with especially with steel. So this is what happens, and we have different consistency classes. Again, we have some categories, and we have some categories also in terms of the composition of the material. Again, we have 5 categories. So we start from a pure Portland cement, so the one which comes out from the clinker. So we have some other cement with more lime, the one which is obtained by a residual of the petrochemical operation. So we have some slag. In some cases, we have some considerable amount of slag. For example, if you make concrete for structures which are close to implants for petrochemical extraction, oil extraction, or similar, we are going to use slag. In other cases, we have some areas which are more volcanic, so we use more porcelain, and basically we have amount of pyroclastic rock. Again, it is given by standards, so you cannot exceed 60%, or you can have a composite works because it reduces prices and it allows the presence of waste. Basically, you get always the most composite a material is. In some cases, the properties are reduced, but on the other side, you are able to introduce a large amount of, which might reduce the price. Here you have an idea, for example, of the approximate range of compression strength with porosity. I don't go into much into details with compression strength because we have already seen it, and basically it's nothing special. You can have some tests with tubes and some tests with cylinders, which are put down a press and compressed, and they are useful until they reach the modulus of rupture, basically. So basically the elastic limit. After the elastic limit, they have little interest. This is not how it is the case with steel. So basically, when you exceed the elastic limit, they tend to be broken. Here we have other work with the cumulative volume of pores and the cumulative volume of pores and the pores diameter. And you can go up to 1 year, for example, and see what happens, because it's interesting also to try. In some cases, the curve is prolonged because they want to understand what happens with over time. In some cases, or in some cases, it might be also the case that it's not effective enough for the composition and water to cement ratio you selected. For example, here to the right, you see a water to cement ratio which is 0.7, which means that we need to have a very workable cement, possibly because we have aggregates of different dimensions and so on. And to the left, you can see also how the cumulative for the standard cure time, so natural drying time usually, you can, natural means in open air, you can have a water to cement ratio that the higher it is, the more you have a cumulative volume of pores with a dimension of pores. Once again, you can see some points, some experimental points, which depend on the dimension of the sieves, basically. And as always, you have to stop at a certain point because we have nano sieves, but they are not. We can make these nano sieves now with materials like nanocellulose, nanopaper. We can make them. They are not always very reliable, but it's still beyond our limit to see 1 nanometer particle just down a sieve, because we don't have sieves with mesh that small. But on the other side, it's not particularly interesting for a material like cement. In other applications, though, this would be very interesting when you talk about nanomaterials and you put therefore nano fillers. For example, in a nanocellulose paper, you can put some very small amount of sand or of similar ceramics. It might be interesting to do that, but in reality, what you can see is take an optical or an electronic, better an electronic microscope observation, but on the other side, you don't take your electron microscope with you when you do this kind of operation. Even in small labs, you don't always have the electron microscope, and therefore working with sieves is much more accurate if the sieve is big enough. If the sieve is it is less accurate, but it gives you the real distribution, although with some degree of accuracy. On the electron microscope, you can just have an idea of the dimensions of the different particles. I'm not saying this is not useful. In some cases it is, and I have used it as well a number of times, but it is not like having a probabilistic or a okay, and so about steel bars, so we are going to make reinforced concrete, and we put some steel bars. You know that we use these bars, which are especially prepared. They are not smooth. They have a number of cavities, or repaired cavities, in order to allow them to provide a better interface, to the best possible interface with the cement. The idea is that the cement is able to penetrate into these cavities and provide some interface and basically bond. The bars work into tension, the concrete works into compression, so they provide a useful mix. In practical terms, we have low carbon bars, ferritic bars, and what happens is that they are oxidized. They are provided with an oxide. We have already done some corrosion some time ago. And just to give you an idea, we have two situations. Here we have an aerated concrete, a concrete where air is able to pass throughout. Again, it's an ideal situation. In a sense, it is the worst situation. The real situation is in between. In practical terms, we have oxidation throughout the most of your curve. So the rising part, it's all about oxidation. The question is, so we are going to have oxide. The question is how this oxide is going to be stable. This oxide is not going to be stable above, say, 500 millivolts. You may remember that we calculated that on a standard electrode based on Camerino. Here we have transpassivation, and basically the thermodynamically stable, and therefore is going to be destroyed quite abruptly. In most cases, we have an oxide which is stable, so we are in a situation of that iron is the anode, but the oxide is going to stay there. And basically, we have oxidation, but not corrosion in most cases. But then there is the presence of sulfates, which contribute to the increase of raising this curve, basically to reduce the area in which well, so this is the two extreme cases: no oxygen and complete presence of oxygen, so air which is able to travel all through our concrete. This is done by a study of porosities. So these are laboratory studies that we find studying porosities, and see. If you take a section, you can see that they are able to travel all around. Of course, it depends on the type of. This is done for every type of cement, in every type of condition, because this is a condition that assumes that there are no salts. There are no salts, so no chloride, no sulfate, and other salts. In other cases, the area in which the oxide is stable much more reduced in practical terms. And and therefore we need to see that, because there is also another question. Also, apart from chloride and sulfate, there is also the question of carbonation. Carbonation means that what happens normally, you take lime and it becomes limestone. Lime, it's calcium oxide, and it becomes calcium hydroxide because it is hydrated, therefore, with water, and you get and then you have the action of carbon dioxide, and you have carbonation, so you have calcium carbonate, which is good. Having calcium carbonate, it would be good in all senses if we didn't have steel bars. If we don't have steel bars, then it's good to have calcium carbonate because it's more stable and tougher and stronger than calcium hydroxide. Okay, so it is structural. But if we have steel bars work because they are in what I didn't specify about the corrosion curves is that they are, of course, they are pH dependent, and they work that well with these steel bars, which are sort of anodized, so they have a sufficient thickness not to allow them to be detached, thickness and stability, and they are not detached from steel at 12.513 because you have a strong acid, strong alkali, sorry, so strong alkali, which is calcium hydroxide. You started from that, and in practical terms, the pH is very basic, and this works very well to avoid corrosion for steel. In other cases, it is decreased at 8.5. It is decreased at 8.5 because from calcium hydroxide you go to calcium carbonate, and which is still alkali, but it's much lower. And what you have, it's really that in practical terms, you have these two effects. You have different degrees of corrosion, which are calculated by the amount of material which is taken away, which is removed from your steel bar. And what is more worrying is that you can see this, in this case, we don't have cavities, we have some parts protruding. And well, this depends on the design of the steel bars. There are a number of types of steel bars. Anyway, the idea is to provide some, we don't do any smooth steel bars anymore because then the interface is so variable, and also because water is able to move around between the concrete and the steel bar. In this case, water has more difficulty to move around at the interface between the steel bars and the concrete. But on the other side, we have to consider that if corrosion arises because the pH is not the one we had before because of carbonation, what happens is that we have a corrosion which is not uniform by any means, so it can take away in an irregular way the steel bar. It is this marked irregularity. It's important as well because of one fact that being so irregular, you can have some effect of kind of necking, and in the end, it will the section will be reduced in a non-even way, in an uneven way. It is reduced in an uneven way, so in practical terms, it might be broken in a brittle way and suddenly. Another possibility is that it is not broken, but for example, you can have an effect of uncovering, of which is called spalling, which is due to carbonation and sulfation. The combined effect of carbonation gives you raised to corrosion, this electrochemical corrosion, is still in alkaline environment, but less alkaline than the one we would need. And sulfation. Sulfation means that you are transforming calcium carbonate into calcium sulfate, which means into gypsum, into chalk. And what happens is that the steel bars are exposed. This is called spalling. They are exposed, and in practical terms, they can be really exposed to the external environment, which means that they may incur into further sulfation, etc., or into presence of other polluting action. For example, at sea, they might be exposed to the effect of salt water. And there has been a number of studies about that. For example, you may remember the question of Ponte Morandi in Genoa, where the effect of salt water was, of course, obvious because chlorine has got chlorine and sodium chloride has got a further effect, which is in an acid field, not in an alkaline field. And so very low pH, this is what we call it pitting, the formation of pits on the small and conical cavities. There is a lot of literature about that. There was a study, for example, about the terrazza Mascagni, which has been one of the first reinforced concrete structure exposed at sea, which was realized in the 30s to honor the local musician Mascagni, and this was completely consumed by. It was restored. It was completely consumed by salt water, and it was restored in the last few years. Then you have here a possible test to identify carbonation, because of course there are some pH indicators like phenolphthalein, and the non-carbonated area can be seen by the fact that it is colored by phenolphthalein, whose turning point is at 9.5. Okay, here two examples of steel reinforcing bars. Steel reinforcing bars, you may remember, gives you an idea of how the things work from an ideal point of view. And in practical terms, we are able to use the steel bars according to their compression, their tension stress into operation. So the tension strength, which is for these two types of bars I'm showing, is 540 and 450 megapascal. And then you can have one which is cold drawn, another which is hot drawn. I remember that cold drawn means that it is drawn at less than 30% of the melting temperature of the iron in Kelvin degrees, and hot drawn it's above 70%. And this gives you an idea of how these two curves work, and in practical terms, what it is expected is that epsilon is the strain is very low. In practical terms, we don't expect very high strains, and that's why we intend still to use this kind of steel, which are also very hard, and they can be drawn quite precisely, because you can realize that the steel bars need to be very precise, because they will be damaged by the effect of corrosion. So we need to start from an interface between steel and concrete, which is as precise as possible. So this is the case of pitting. Some cases of pitting, I would say pitting is in, for example, in presence of salt water, or in the presence of acid attacks, of strong acid attacks, in the presence of strong acids. In fact, there are some environments in which concrete is not. There are some industries working with chlorine, where the use of concrete is not recommended. They tend to use steel bricks, etc., to make their buildings, because steel offers these possibilities of quick corrosion by pitting, so by the formation of these pits. There are pits which might be even deeper than that, and have a real conical structure. I have shown you that into. This is a consequence, because we can produce concrete with some potable water, drinking water. In other cases, we don't produce concrete with drinking water, because we are not obliged to do that. Because you can understand that drinking water costs more, and we use lots of water to produce concrete. So in practical terms, in some cases, it's better to use a non-drinkable water, so-called industrial water. So water you can use for some industrial operations, but cannot be drunk. And we cannot do anything we like, because in reality we need, if we don't use drinkable water, for drinkable water the chemical analysis is standard. You don't have drinkable water if you don't have analyzed it. You may know that on any mineral water, but even on your tap water, there is a chemical analysis, which has been done in advance, because of establishing that it is drinkable, and it is repeated every some time. Be sure that it stays as drinkable. You can use industrial water, but then you need to provide evidence of analysis. For example, sulfates needs to be less than 2,000 parts per million, alkali less, etc. And some substances, there are stricter requirements. They have some other substances like sugars, phosphates, nitrates, lead, which need to be virtually absent, because they form complexes with calcium carbonate, and which might lead to even more complicated situation in terms of affecting the concrete and corroding the steel bars. The last few minutes, I would spend the last few minutes to make you understand how in practice these things work, how do we decide which kind of concrete we use. So we have here the characteristic. I have already shown a part of this before. So we have the water to cement ratio, which appears to be the controlling factor, because as I was saying, it's the only one which is really controlled at the time of the production of the material. The concrete is different from other materials, in the sense that other materials we can also, for example, steel, we can control any parameter we want. We can control the temperature, the pressure, even the environment, because we decide we are going to perform that in a definite environment outside the control. This is even worse for polymers. In polymers, we control anything because the temperatures, melting temperatures are lower, and therefore we need to be very careful about, for example, the entrance of air trapped, etc., because air bubbles in polymers might be devastating. So, and porosity. So, concrete is completely different in this sense. We have the water cement that controls durability, that controls strength, durability, so how it's going to last over time. Strength is the initial strength, of course. Workability and cost. There are also some technological measurements of workability. You can, if you are curious, you can look around. There are a number of technological ways of, apart from measurements of viscosity and measurement of the kind of biological behavior, you can do some technological tests like the ones on this lab to see if the material is sufficiently workable. Of course, this depends also on the type of aggregates of the diameter, etc., maximum diameter, so studies with seams, etc. But we can start neglecting the effect of aggregates and basing all your design on the selection of WC ratio, so water to cement ratio. This is called the mix design. So you want the most appropriate mix of properties, and these are the properties. In more practical terms, the properties are the material type, the class of compression strength, because depending on the type of structure and on the geometry of your structure, you want to have different compression strengths. Environmental exposure, which is becoming very important. The fact that you are in an area which freezes, where water freezes at night, so you are likely to have temperatures below zero. You can have salt water. You can avoid, for example, the penetration of water. You are not in a saltwater environment, but for example, you are making a dam, so it's not salty water, but you need to avoid that water penetrates. And other condition, for example, you want to another protection of the reinforcement, because you are required, for example, to use a limited thickness of your concrete above your steel bars or steel net. If you are obliged to use a limited thickness, so then you have to add the protection of the reinforcement, avoiding corrosion. Then slump, and also the maximum diameter of aggregates is established. Otherwise, you don't have any more concrete, because the idea is also that there is also a maximum diameter of aggregates, because the idea is that cement has to go around the whole volume, the whole surface area of your aggregate, which it might look easy for you if you assume that it's spherical, but usually it's not spherical. It is very complicated, and so, for example, it has been crushed and then used to concrete. It might have a very, very large number of sides, and therefore it might be difficult to allow cement to go around the whole surface area. And which means in practical terms that we have to stop at a certain point. Of course, it would be nice if we could use into concrete any kind of aggregate, because this would reduce the cost. It is not possible to put aggregates of more than 20-30 millimeters maximum diameter. Of course, you can also introduce the question of durability and shrinkage over time. Because over time, whilst other materials tend to delay, like it is the case for polymers. Polymers tend to expand a bit, to extend a bit in terms of lengths. Instead, concrete tends to shrink, because it becomes drier and drier, and in practical terms, the pores tend to close. Also because there is a weight applied on it, usually. That's why all these tests on slump and to allow understanding whether the wall is safe and will not collapse. So we can have, in this case, closed and open condition. Closed condition means that there is just one only condition. For example, I want to use this kind of cement, this type of cement, and I will adapt the other characteristics. I only use this type of cement because I have seen it works in this environment, or because I can use it. Simply speaking, I have to adapt all the rest to my cement. Or you can have an open solution where we can have all possible combination, a number of combination. And usually the one which is always kept constant is the class of exposition, because in the closed solution there are some situations may produce a very nice cement, but for example, a very nice concrete, but we cannot be used at sea, for example. In the other case, if I have open solution in which I can accept different types of combination of factors, I need to keep constant, for example, the class of exposition, not for example, because I need to apply an open solution is done to apply in a definite place. So I, in a definite place, have my cement. So a closed solution is more for routinary building. So I have this cement, I know I can do a number of different works. Open solution is more dedicated when I'm doing this important and costly building, and therefore I need to consider all the factors. And I know that the environment is this one because of the images, for example, Camerino and so on. Open solution, it makes easier to consider cost and environmental impact. Because in closed solution, for example, if I use the same concrete to build 10 houses, 10 buildings, well, it's tricky to understand the environmental impact also because in some cases it's even difficult to understand how much concrete I use for that building and how much concrete use for that other building and so on. Even this already is difficult to understand what is the cost because possibly I pay for the whole of it. And the environmental impact of the production in a combined number of building sites is more difficult to understand what is, for example, the waste, the amount of waste I produce, the amount of energy I consume, and the amount of water and the quality of water I use. Because in a closed solution, I often use, simply speaking, the water I have available, so in most cases drinkable water to simplify things. This increases the environmental cost, this increases my own cost, which I can discharge on people, which download on people which are going to buy, for example, a flat. So durability is becoming more and more important. Durability is becoming more and more important, and so I need to adapt the water to cement ratio to the combination between durability and strength. So it depends whether if I have a high strength cement, so the water to cement ratio for durability is higher than the one for strength, I adapt to the one for strength. If the water to cement ratio is for durability is lower than 1 for strength, I adapt to the former. So I have a low strength cement. In this case, it is resolvable because I take two indications, durability and strength, and I adapt to the water to cement ratio, the lower water to cement ratio, provided it is workable. It needs to be sufficiently high for cement to be workable, and then I adapt to the one that gives to me a that puts me less into trouble, because basically if I have a low strength cement, I have to adapt to increasing the strength of cement, and therefore I have to reduce the water to cement ratio. In the case, I try always to reduce the water to cement ratio, provided that durability, that workability is ensured. Okay, in some cases, it's not possible to reach the water to cement ratio sufficient for any of the two applications. So that's why I have the question of which this time I have to buy something else. Because in some cases, for example, the water to cement ratio which I use is not sufficient to make the material workable, although it would be preferable to reduce it to that level. But then the material is not workable, and then I have to interact with other factors. I could also act, for example, on the dimension of aggregates, on the distribution of aggregates, on the use of other aggregates, and possibly even to change cement class, although it is a difficult situation because the class of cement have different costs. I will always go for a composite cement because I can mix, it's more easily mixed with other waste, and being less pure, it costs less, but it might not be adapted to this situation. Or to say it better, I might not have a water to cement ratio usable with this kind of cement, which is adapted also to the two situation of strength, sufficient strength and sufficient durability. Okay, I close with this slide to show you that strange things are happening, strange things in two brackets, strange things are happening, but important things are happening. I may have mentioned to you that waste is introduced, the two main materials in which waste is introduced are basically cement and asphalt. And we can see here one of the examples, which is a study, an experimental study, but which gives you an idea of how things work. I can have a quite interesting material like nanosilica, which used as an abrasive, but a wear-resistant material, so silica in very small particles. It's very diffuse anyway, and it generates its production generates quite a lot of waste, so it's not that expensive in the end. Then I have keratin waste, in practical terms, human hair. I know it appears a bit odd, but we have a lot of human hair which ends up from hairdresser and so on, which end up into landfill. So why not using them into cement? They are stiff into tension after all. And other materials which are stiff into tension are coconut fibers, core fibers, which are materials which are also used, for example, for doormats, but you need to consider are a part of the coconut industry. And coconut industry is an industry which has got a number of products for food industries which are very expensive, and therefore waste is easily obtained. You can find a very large number of these kind of studies trying to see whether introducing waste in concrete, I reduce the cost, but then I am able to keep the same performance. Here, what they have done is a compressive strength, of course, and after due time, 7 days and 28 days, of course, the compression strength increases with due time. I assume that at 28 days we have to stop. But of course, if we are able, 28 days is the minimum one. But if you want to leave your wall covered for 1 year, that would, of course, improve the compression strength. But the law requires 28 days, apart from particular situation. But in normal situation, it requires 28 days. And then it compares the different sample series, so different amounts of core fibers, human hair, small amounts, because of course you start very cautiously with waste, but the idea is to put as much waste as possible. Then they have done some cyclic fresh flexural strengths. Basically, they've done some flexural strengths, but also some cycles, which produce the results. Here are the broken samples, the broken beams, so flexural strengths. So basically, it's a beam. Whilst the compression strength, you may easily imagine it was a cube, more than a cylinder, because these were quite high thicknesses. And here you have a beam which is a 3-point flexural test. And they have done also cyclic flexural tests for a few cycles, because, well, this is not like in steel. We do some flexural tests here on concrete, but for a few cycles. You wouldn't expect that to withstand millions of flexural cycles. Because it's usually part of a larger structure, and also concrete is not the right material to withstand millions of flexural cycles. But anyway, this was done for a few cycles, and of course the introduction of different waste produces some differences, even if waste looks very little, even if you introduce just a little bit of them. Be cautious, but you can see that in some cases you improve a little bit between, for example, the D appears the best one for flexural strength when you introduce 0.75 of core fiber, 0.75 of therapy fiber, and 3% of nanosilica. So as always, you try to make different compositions and see which is the most suitable for your application. So here you increase the flexural strength. And in some cases, the introduction of waste might be good. The introduction, not just in terms of cost, but also in terms of LCA, or life cycle analysis, of course, but also in terms of improvement of performance. Because in this case, it's obvious they provide a little bit more hardness with nanosilica, less porosity, more hardness, and a little bit more of tensile strength of core fiber and keratin fibers provide tensile strength. So this is promising in terms of use of waste in this kind of materials. Next time, which is going to be on Monday at 4, we are going to concentrate on, I stopped with beam, with this kind of beam, and of course we carry on with other kinds of beams, so with wood. Next time we are going to concentrate on wood, and then we are going to close the course on talking about the polymers and composite like carbon fibers and glass fibers. Okay, so have a nice day, have a nice weekend, and as always, I will put everything on YouTube, the recording, and going to be on my my web page on the website. Have a nice day.